We present a way of controlling a CNC milling machine for wood using a computational notebook and an augmented reality interface. Our system, called Imprimer, helps makers interactively learn and experiment with milling techniques that aren't focused on replicating existing 3D models. Such exploratory workflows include working with novel materials, experimenting with generatively designed patterns, and creating an engraving by mapping an image's pixel values to engraving depth. Conventional CAM software like Autodesk Fusion 360 or Vectric Aspire provide a great deal of functionality, but sometimes also pose issues for learning and exploration, especially for non-professionals. Conventional tools often have a steep learning curve, where makers need to understand the many machine parameters before cutting anything at all and learning what they need to change. In addition, unconventional workflows like improvisational cuts or high-level parametric designs are difficult. Instead, we draw on literate programming, a paradigm popular with scientists for exploring data, to imagine an alternative way of controlling CNC machines. While we can't expect to support everything that established CAM tools can do right now, we can instead focus on fundamental setup and cutting operations. This is a basic workflow implemented in an observable computational notebook. It uses Imprimer's machine network to establish a direct communication between the notebook, shop-butt CNC mill, and the AR overlay. Direct control can pose safety risks, so we write pre- and post-condition functions, such as requiring that a machine's tool be above the stock material, which are then checked before the maker can dispatch certain moves to the machine. Makers can use various live views, such as this 3D toolpath view, that update automatically as notebook cells are changed. Makers can understand how machine parameters such as feed and speed are calculated by examining source code and editing it as desired. Switching to a view of the notebook alongside the shopbot, the notebook interactively walks us through zeroing the machine, updating the notebook state in tandem. After we've set up the AR overlay, we can sketch a shape, for example, the C in Chi, and visualize exactly where the C would be cut on the stock material. Once we check the safety preconditions for running the machine, including turning on the dust vacuum and donning safety gear, we dispatch the cut directly from the notebook, rather than having to export and import as we usually would with most CNC mills. We repeat the process with the H and Chi, adjusting it as necessary. After cutting the H, we notice that the finish is rougher than desired. The notebook contains a section on troubleshooting finishes. While there could be several issues, like using an upcut end mill as we did here, we alleviated the issue by limiting the feed rate to 90% of the initial value, as recommended by the ShopBot user manual. We then cut the I and Chi using the new feed rate and sketched an organic surrounding shape to be cut out completely. Using a slider in the notebook, we updated the cutting depth variable, which updates both the depth visualization on the AR overlay, as well as the 3D view in the notebook, which the maker can inspect and dispatch when ready. After sanding off the finish, we had a quick prototype that was fabricated in under 10 minutes. As a more involved example, we implemented a parametric shelf generator entirely in a single notebook. We can adjust the height, width, depth, material thickness, and shelf spacing of the bookcase and see a top-down view of the parts update live. All toolpaths are generated as functions in the notebook, which makers can inspect and modify if needed. After fabricating one shelf, we noticed that the rabbet joints fabricated were slightly shallower than expected. While several techniques could address this, we wrote code to generate test pieces and cut several out with different depths before determining the best one for the material. This resulted in a much better second iteration, and by solving the problem computationally, we've documented our process for others to use in the future.